In today's class, we're going to look at the derivative as the instantaneous rate of change. Now we're also going to look at the average rate of change and also how that relates to the instantaneous rate of change. But if we have some function f of x here, and you can see that it's graphed here or plotted here, if we wanted to find the average rate of change from these 2 points, here's the origin, so x is 0 here. So the x value here is 2, and of course here it is 4. If we wanted to find the average rate of change, what we need to do then is to look at the secant line between these 2 points. So if we draw the secant line, this should be very familiar from what we've talked about before, and if we draw the secant line, that will be the average rate of change. When we're doing the average rate of change, sometimes the points may be side by side. They may be 100 100x units apart. So we can't just simply take the 2 numbers and make the average and say that's the average rate. Because after all, rate also incorporates some element of time somehow. Now, doing the secant line would give us, or finding the slope of this line would give us the average rate between these 2 points. So we could use our slope formula and plug in, this would be our x sub 1 and our y sub 1, and our x sub 2 and y sub 2, put it into the formula, and we have it solved. So that makes it easy. Putting this into a business situation, it's possible that here we want to find out the average rate of change from going from our current production level here at x is equal to 2. Say maybe that's when we're producing 200 units of something. We want to find out if we were to produce 400 units of something, when x would equal 4, if x is in 100s, to find the average rate of change that we would have to do to get from 200 to 400 would be this line. So that's what we're doing here. Now, of course, when we're doing this, we're actually calculating the slope, and the slope is the derivative, but since it's between 2 points, we calculate the average through the secant line. Putting it into calculus terminology, instead of using the slope formula, which we can do, putting it into calculus, x sub 2 is f of b. In this case, using this formula, a and f of a would be your smaller x value. In this case, it would be 2. And b is going to be the greater x value. And in this case, x or b would equal to 4 because we're doing an x of 4. So what we would do here is do an f of b, and f of b is going to give us this y value, which again, this is 3, means that the y value would be 4. And then we subtract an f of a. Well, an f of a is here an f of 2, and that would be, in this case, 1. So we would take the 4 minus the 1, and realize that that's the same thing as calculating the slope, of course. And then over b minus a. If this is b and this is a, the distance here would be 2. 4 minus 2 would be 2. So we could calculate the slope by taking the rate, the change in y over the change in x, or this formula. Now, using the average rate of change, it's relatively simple. If we wanted to calculate the average rate of change over the interval from 1, including 1, up to 2, the average rate of change from 1 to 2, including both of those numbers, the smaller number, again, we would say that the smaller number is our a, and the larger number is our b. So we do an f of b. If b is 2, we do an f of 2, and we're putting it into this function here. So 2 squared would be 4, and we subtract an f of a, and again, a is 1 here. So 1 squared, of course, is 1. And then we're dividing it by b, which we said was 2, and a was 1. So we get a difference of 3 over 1, or an average rate of change of 3 over this interval. Now, continuing on, if we made the interval smaller, say we wanted to find the change of rate, the average rate of change over the interval from 1 to 1.11, including both those numbers. Well, now our b is this 1.1, and our a is 1. So we put it into the formula, and we get this 1.1 squared minus 1 over 1.1 minus 1, and we get 0.21 over 0.1, so the average change is going to be 2.1. So we see over that interval the change is different. Over the entire interval from 1 to 2 is 3, over the shorter interval it's 2.1. Now, as you can kind of see, what I'm doing here is making the interval smaller and smaller. So if we change our b to 1.01, well, that's going to make the change even smaller as well. And so if we put this into the equation, our f of b is this minus our f of 1. Again, we're putting it back into this function, so it's 1.1 squared, and our f of a would be 1 squared over b minus a, and we get a value that's closer and closer to 2 as we get smaller and smaller. Well, we're beginning to see, I'll actually introduce it more formally later, but we're beginning to see that as we make the change smaller, that we get closer and closer to the derivative. After all, if we take the derivative at x is equal to 2, we get 2. Or excuse me, x is equal to 1, we get 2. When we're doing this, just to be clarified here, since I said that a little bit funny, each of these times we're starting here when x is at 1. So if we take the derivative of f of x, if we find f prime at 1, it's f prime is going to be equal to 2x, and if we do an f prime of 1, we of course get 2. And we notice that as the change gets smaller and smaller, we get to the derivative. So the average rate of change, we use the slope formula, or now the calculus version of it. But we realize that as the change gets smaller and smaller, we're coming closer and closer to that value, or what we sometimes call the instantaneous rate of change. Now, again, this is the formula for the average rate of change over a specific interval. And again, if we look at this, we have the secant line, and we can use the secant line derivative formula to work with this. But we realize that as h gets smaller and smaller, as we bring the change closer and closer back to the original point, well, we know we're going to get the first derivative. We've talked about this before. So as h gets smaller and smaller, we're finding the instantaneous rate of change. The rate of change, the green line down there, is the tangent line at that point. It's also the first derivative at that point, our f prime of a. So if we're looking at one particular point, then we're looking at the instantaneous rate of change. What is the rate of change at that one point right then and there, the instantaneous, right now, so to speak? If we're currently producing that number of units, what is our instantaneous rate of change? That's the rate we have right now. If we're looking for change between 2 points, from this point to this point, oops, excuse me, then we're looking between 2 points, and that's going to end up being the average rate of change. Now, when we're looking at this again, if we're looking at the average rate of change between A and B, we would find this line, the secant line. If we want to find the instantaneous rate of change, well, then we want to find the slope at just the point we're at. In this case, point A. So the instantaneous rate of change is going to be the tangent line at that point. And so the two can have very different values. They can also be very close, but oftentimes they will be different. Now, trying to apply this to a situation, we're looking here at a graph of the population in the U.S. in basically the 1800s. So the first line here is 1800. This would be 1810, 1820, 1830. So in 1840, we would say the x is equal to 40. The y value here is 17. So that means that there's going to be 17 million people who lived in the U.S. in 1840. Now, if we wanted to find what the average growth was, now with the average growth, again, we're looking at two different points. So the first one is at 1840, and we want to find the average growth of the U.S. population from 1840 to 1870. So we would find here out in 1870, x is equal to 70, and we realize, oh, well, up here, it nicely crosses there. It's easy to see. The population in 1870 was 40, again, million people. So if we want to find the average growth, we draw the secant line through here, and to find that value, we simply use the slope function, or again, using calculus terms, the average growth formula. So it's f of 70 minus an f of 40 over 70 minus 40. And once we do an f of 70, we said it was 40. We said an f of 17, an f of 40 was 17, and then 70 minus 40 is 30. So do the simple math here, 23 over 30. It's approximately, the average growth rate was approximately 0.77. Now again, that's millions of people. The average growth per year, so to speak, or excuse me, not so to speak, the average growth per year would be 0.77 million people, or 770,000 people per year. Now, how fast was the population growing in 1840? We don't want to find the average here because we're looking at just one point. How fast was the population growing in 1840? Well, we're looking for the growth in one specific year at one time. That would be the instantaneous rate of change. So the instantaneous rate of change is to find the first derivative. Now, unfortunately, in this example, we don't have a formula for this. We don't have what the function is in terms of x's and y's. But what we can do, since we have a graph, is to graph the tangent line. Now, the slope of this tangent line will be the first derivative, and the value of it at this point will be how fast the population was growing in that year. Since we don't have the formula, we have to find the slope of this line. So it feels similar because now we're finding the slope of this line versus before we were finding the slope of this line. But to find the slope of this line, we find a second point, and out here in 1890, the population was 42 million, and we have this here. So since we're doing a straight line, we can use, again, the slope formula. So y sub 2 would be 42, or an f of b minus an f of a, or x sub 1, or excuse me, y sub 1, and over b minus a, or x sub 2 minus x sub 1. So again, this is going to be 0.5, and again, how fast was it growing? Well, that's going to be 0.5 million people per year. Again, whenever we have a rate, it's always involved, some kind of time is involved. In this case, it's the number of people per year, or number of people divided by the number of years. And so that works out to be 500,000. 0.5 million, 500,000 people per year is the instantaneous growth rate in 1840. Now, was the population growing faster in 1810 or in 1880? 1810 is here. 1880 is here. Well, we're not asking for the average change here. We're simply asking, is it growing faster in 1810 or 1880? So what we want to do is to compare the instantaneous rate of changes. Compare the slope here versus the slope here. Now, again, if we had a formula, we could simply do, for example, an f prime of 1810, and compare that to an f prime of 80 for 1880, and we'd have our answer. But since we don't, in this case what we need to do is to look at the slopes. And we look at it and estimate that, well, yeah, we think it would be growing faster in 1880. Well, if we draw the tangent line here in 1810, the tangent line would be here. And if we draw the tangent line in 1880, it's going to touch here at this point, it's like this. Now, again, the steeper the line, the greater the number, right? So, if this was a number, we would say it looks like it's a little bit more than 1, a change in a little bit more than 1 over 1. And this one, the change is much slower. It looks like it's going to cross down here, or, let's see, it's at this point. Oh, look, it goes up about a half. It would take a long time for it to get up over here. So it looks like the change is going to be 1 over 1, 2, 3, 4, 5, 6, 1/6. Well, 1 is greater than 1/6, right? So the slope is steeper. Wherever the slope is, the incline is the steepest, that will be the fastest rate. So the population is growing faster in 1880 because this red line is steeper than it is this line. This rate is growing faster than this rate. Now, when we've been talking with the derivative, trying to apply it to settings, we've said that derivatives can be the instantaneous rate of change, what we just discovered now. And in business, we can use this in different ways. So these are business applications as well. We've also said in prior classes that the derivative is also our margins, our marginal cost, our marginal revenue, our marginal profit. Now we're also going to look at the derivative being the change in a function, the change that occurs in a particular function. Now, when we're looking at the change in a function, you may say, well, what do you mean by change in a function? Well, for example, you're working for a company and your supervisor decides to hire 30 new employees. And he comes and says, well, if you have 30 new employees, how many more units can you produce with these 30 new employees? That is the change in a function. You have a certain number of employees, you're going to add 30 to it, you're changing the function, and it also has implications to your cost. Another example, if you produce 500 Kindles, well, how much increased cost will there be to produce 502 Kindles? That's a change in a function. In this case, change in your cost function. So it's that kind of thing. Now, when we're working with change in a function, where h is the amount of change, again, with the Kindles, we wanted to produce 2 more Kindles. H would be 2 in this case. We could look at it and say, well, the amount of change, well, if we were producing 500, A would be 500. 500 plus 2, the cost of producing 502 minus the cost of producing 500, well, that's the amount of change, right? Well, this, when we're working with this, if we look at the slope at 500, the f prime of A, and multiply it by the change, it's the same thing. We'll see this in just a minute. It can be helpful when you're working with this to think of it as this f of b minus f of a, since we're used to using that rather than working with the secant line. But if you were producing, let's use a different example. Suppose you were producing something that cost 5 litres per unit. That'd be your marginal cost. It cost you 5 litres per unit to make these things. Now currently, let's say you're making 6 of these an hour. And you want to find out, well, how much increased cost would I have if I produced 10 per hour? Well, you could say, well, I want to produce 4 more units. 10 minus 6 is 4. Well, each unit, of these 4 units, each unit cost 5 litres to produce. So I would take 4 times 5 and say, oh, it's going to cost me 20 more litres. Well, that's what the increased cost is going to be. That's what the change in your function is. If you know what your cost function is, you can figure your marginal cost. that would be like the 5 liters per unit times the number of units more that you're going to produce, the change in the function, 4 more units. 5 times 4 would be 20. So that's what we're working with here. Now, here's a graph, and cost functions are similar to this kind of thing. It's kind of a general one. And if we were to find out here, find the tangent line, find the first derivative at this point, if this, going back to our example, if this was, we're currently producing 6 units, and it cost 4 liters per unit, and here was 10 units, we would find, okay, the increase, there's 4 of them. We take the slope at this point and multiply it by 4. The slope at this point would be the marginal cost. That would be 5, and then multiply that by this 4 increase of 4 units. So from 6 to 10, we say, oh, that's very close. That should be accurate. So it's very good for finding values when it's very close and when your increase is pretty steady. If we do it over here, though, say here this x was 2, and we take the slope here, well, this slope of this line, and say if it's some value, and let's say that we wanted to produce 4 more units here. So we come over 4 more units, 1, 2, 3, 4. I say, oh, wow. Well, if we take the marginal cost here and call this a value and increase it by 4 units, it's going to be way up here. It's going to be farther off. So actually, this change in a function is an estimation of it. Towards the end of the class, we'll find a little bit more accurate way to predict it more precisely. But for now, we will work on the change in a function. We realize it's going to be something that is close to the cost. The difference here is not as close as it was in this example. So if you're at a point of rapid change and you're estimating the cost of the function, you probably only want to estimate a cost for 1 or 2 or a few points here. And once you get above that, you realize that your estimation is going to be further off. If you're at a point where there isn't much change and growth is kind of consistent, well, then you can take a larger amount and feel that it's going to be accurate. So back to this, the change in function, you take the derivative of the function at the point where you currently are times the change that you want to do. Here's a sample problem. Let the production function p of x give the number of goods produced when employing x units of labor. Now, x units of labor, not exactly sure what that is. You could say, well, maybe that's people when you have 100 laborers working. Or maybe it's hours. Some larger companies may define a unit of labor as 15 minutes. So that they can figure in part-time people and things like that. But whatever it is, it's a unit of labor. Suppose 5,000 units of labor are currently employed, and we're told that a P of 5,000 equals 300 and a P prime of 5,000 equals 2. Well, what does a P of 5,000 equal 300 actually mean? Well, if we go back to this, the P here, P of x is the production function. Okay. So P of x, when we talk about P here, it's production. And P of x gives the number of goods produced. So P of x, if this was x, equaling 300, would be the number of units that are produced. And that's when employing x units of labor. Well, the x is inside the parenthesis here, right? So it's P of x. So the x in this case is 5,000. So x is units of labor, and x is 5,000. So that must mean that there's 5,000 units of labor that are being put into producing whatever this is. This is the production function. So when you put in 5,000 units of labor of production, you're going to get 300 back. 300 what? Well, again, the production function gives the number of goods produced. So it's going to be 300 units, whatever it is that we're producing. So another way of saying this a little bit more neatly is when 5,000 units of labor are employed, when you work for 5,000 units of labor, 300 units of goods will be produced. You'll make 300 units. Now, what does P prime of 5,000 equals 2 mean? Well, again, the 5,000 is staying the same. It's in the X position. It's a unit of labor. So when we have 5,000 units of labor, P prime, well, P is our production, and anytime we're doing prime, it's the derivative, it's a rate. So it's the production rate. So the production rate will be 2. When we have 5,000 units of labor, the rate of production, the production rate, will be 2 to what? Well, again, we're still using the P function, right? So it gives the number of goods produced. Oh, so it's going to be 2 units, but we remember that it's a rate. Rate is always over time. So it's going to be 2 units produced per unit of labor. X is equal to units of labor. So when 5,000 units of labor are employed, when 5,000 units of labor are worked, the rate of production will be 2 units for each unit of labor. You say maybe it's 2 units per person if the unit of labor is a person, or it's 2 units per hour if a unit of labor is an hour. Increase the number of additional units of goods produced when X is increased from 5,000 to 5,000 and a half units of labor. Well, we're going to increase by half a unit of labor. How many more additional unit goods are we going to produce? Well, we're going to use this formula. In this case, P prime at A of times H. What is P prime of A? Well, we're going to do P prime of 5,000, right? Whenever we're doing this, we're looking at our current rate of production, and that's at 5,000 units. So we want to do P prime of 5,000 times H. What's our H? Well, P prime of 5,000 up here we're told is equal to 2. Our H, then, we always look at it to say, well, where do we want to be? What's our goal? What do we have in mind? What do we want to do? Well, we want to produce 5,005. We're going to subtract our current amount here. Currently, we're producing 5,000 units of labor, we're told here. So 5,000 and a half minus 5,000 is a half. And when we looked at it, we realized, oh, well, this makes sense. We want to increase from 5,000 to 5,000 and a half. The increase is going to be a half. So you can look at it and figure it out. But if you're going to use the formula, just make sure that this is the current amount, and this is the value that you want to have. So P prime of 5,000 is 2, H is a half, so we multiply them together to get 1. So that means 1 additional unit is going to be produced. And that's, again, when we put in a half a unit of labor. Now, that answers this question, but maybe we also want to find out, well, what's the total goods that we're going to produce if we increase this extra half unit of labor? Well, then we have to come back to here. Our current level of production is 300 units, so that's where we get to 300, plus the increase, and we calculate that to be 1. So now we're going to make 301 units. So the change in the function would be how much change we're going to see in additional units, and that has an effect on the total units. If we're currently producing 300 and we produce 1 more, the total is going to be 301. Now we know that we want to do F prime at A. In this case, it's going to be the marginal cost, C prime, at 10. Why is it 10 instead of 1,000? Well, we have to go back to our problem. The cost is in thousands of liters, but the production in units is in hundreds of units. So to find out how many X's we're going to use, what the X value is, we currently have 1,000 units. We simply divide it by 100 to get 10. So when we put 10 into the formula, we will be finding the value. Even though X is 10, it's in hundreds, so we know that that's going to mean 1,000 units. The key to this is if you have a value, again, 1,000 units, if X was in thousands of units, then we would take whatever our current amount is and divide it by 1,000. In this case, it's in hundreds, so we take whatever our current production is and divide it by 100 to get 10. So we need to keep that in mind. The formula has to have x's in hundreds, so we take the numbers that we have and divide it by 100. So we do a c prime of 10 times h. The first step, of course, we need to find the marginal cost function. So we look at this and say, well, that's going to be 12x plus 2. And then we do a c prime at 10, and we get 122. Now remember, the total cost and the marginal cost will be in thousands of liters. So it's 122,000 liters. Now, our x's are in hundreds of units again, so we also need to convert this. If this is 10, we take the number divided by 100. We do the same thing for where we want to be. 1,050 divided by 100 is going to be 10.5. So we take where we want to be, 10.5, minus our current to get 0.5. So this changes our answer from what we initially thought. We have to remember our x's may be in hundreds or thousands or millions, and cost can be thousands or millions or other two, and we have to apply it here. So now, the last step, of course, is to do the full c prime of 10 times h. 122 times 0.5, cut it in half, is 61, and again, it's in thousands of liters. So the additional cost incurred from going from 1,000 units to 1,050 is 61,000 liters. And if we wanted to approximate the total cost, well, we're not told what our current cost is, but we're given a formula. So our current cost plus the additional cost will give us the total cost from this change in a function. So we do a c of 10, and when we put that in, here we're going to get 6 times 100 plus 20 plus 10, so we get 630 plus 61, 691, and again it's in thousands. So the total cost of producing 1,050 units is going to be 691,000 liters. So the change in a cost function isn't too difficult. Just remember that when you're doing it, look at your x's and your y's. If it's in hundreds or thousands of units, that has to affect your x. If it's in thousands or millions of liters, well, then that has to be incorporated into your answer as well. Now, here's the homework. We're coming from section 1.8, and also a few extra supplementary exercises. If you look after section 1.8, you'll see the supplementary exercises, and I also have a homework supplement on Moodle. Just found in the past that there's not quite enough practice for students to feel comfortable with the change in a function and how it applies. So I've added a few that will help you be more prepared for the exam, which is coming up soon. And again, this is on Moodle.